Welcome to the session 6 of our Unit 1, our financial modeling course. In session 6 of Unit 1, we are going to consider the efficient market hypothesis and the predictability. This is a continuation from our financial distribution and efficient market hypothesis session, that is section 5. By the end of this session, you should be able to differentiate between random walk and Markov process, explain the long memory behavior of asset prices, and finally, empirically test the efficient market hypothesis using the variance ratio test. You could clearly remember from our previous session that we spoke about the efficient market hypothesis, where we discussed how the financial market is efficient given that it cannot be predicted. That is, the past or previous prices or returns cannot predict the future or potential prices. The same way happens, or one way of examining the efficient market hypothesis other than the autocorrelation test has to do with the random walk. So by random walk, we are simply saying that we are looking at a stochastic process in which future steps or directions cannot be predicted on the basis of past action. So we are looking at our previous prices or previous returns not being able to predict our current prices or our current returns. That is, we are saying that it's like a portfolio. So let's say by random walk, we are simply saying that if we are dealing with the stock price or price of any financial asset, when we say the price or the return exhibits a random walk, we are simply saying that price one cannot be predicted, and aside the fact that it cannot be predicted, then the price or the returns are only encapsulated, or those returns or prices are only captured in the current portfolio. So let's assume the prices are portfolios. So we are saying that a particular portfolio, let's say today portfolio 1, let's assume the portfolio for today is a portfolio 1. We said that any information in that portfolio is only linked to its respective day or day. So today, any other information with respect to the price of the stock or that financial asset is only captured, or it only represent today. Any other day has different or has its own or its unique information. So in the stock market, for instance, a random walk simply means that short-run changes in stock prices cannot be predicted. This is what we also consider as the Markov process, where we are saying that the market has no memory. So meaning it's like assuming human beings, when we say someone has no memory, it simply means that the person cannot remember what happened in the previous day. So like you are walking blank without having information or knowledge of what happened in the previous day. So the same thing has to do with the efficient market hypothesis, where we are dealing with the Markov process. So by Markov process is like the walking of a drunk person, someone who is drunk. You can't predict what he or she or the next step of that person. So it's like saying the person has no memory of what he or his previous step or the last step that he or she took. So that is what we mean by the Markov process, which is also a way of examining the efficient market hypothesis. So the random walk and the Markov process are the two most important empirical or mathematical theorem associated with the efficient market hypothesis. The assumptions of a random walk. The following assumptions holds for a random variable RT, which could be any financial asset, by a random walk. One, we are saying that the random variable RT are independent. So by independent, we are simply saying that the return series are not dependent on each other. So the previous returns has in no way able to or cannot predict the current, and the current cannot predict the future. Also, we are saying that the random variable RT are identically distributed. So by identical distribution, we are simply saying that the statistical properties of that asset, like the mean, the standard deviation, and other attributes of the probability distribution, do not change over time. And finally, we are saying that the random variable RT have finite variance. So we are saying that the variations in the variable or the returns of the variable are finite. So random walk can be tested by the serial correlation test among others. So we have a test of serial correlation. So here what we are saying that for an asset to exhibit a random walk, we are saying that that asset should have zero serial correlation. It should not be correlated, and also it should not be correlated. So when the serial correlation results indicate that the asset has zero autocorrelation, then we can presume that that asset has or is a exhibits random walk. A test of random walk. Figure 1.11 is also another autocorrelation function plot which indicates the existence or otherwise of serial correlation, or which indicate that the asset returns exhibits random walk. You could clearly see that unlike in figure 1.9 and 1.10, all these vertical lines are found within these boundaries. These are the boundaries or the limit that was set for the return series. So for us to indicate or for us to conclude that the asset exhibits random walk or has zero autocorrelation or zero serial correlation, we simply want to see these vertical lines to be found within these boundaries. In the previous figure, that is figure 1.10 and 1.9, we rather saw that these vertical lines were outside these boundaries. They were outside these boundaries, which indicate that the asset exhibits serial correlation or autocorrelation. But in this case, in figure 1.11, we could clearly see that these vertical lines are rather contained in these dotted lines, which are the boundaries. These dotted lines, this one and this one, represent the boundaries. Therefore, if the vertical lines are found within these boundaries, then we can clearly say that the test of random walk holds for that particular asset, or the asset exhibits zero autocorrelation. Equation 1.11 is a simple autoregressive model with all the properties of a random walk, where we have IID, which is independent and identically distributed, and our mean is equal to 0, and our standard deviation is finite. We can also understand that the above equation will only be a random test, or will only be considered random if the beta component is equal to 1. This can also be tested empirically under the regression model or using the regression model. A key diagnostic tool in time varying clustering, which is the volatility clustering, has to do with the autocorrelation to squared returns. It has been established that using the squared returns in computing the autocorrelation test is quite perfect, or it has some properties above using the absolute returns. So equation 1.12 depicts an autocorrelation test, or the process that an autocorrelation passes through. Just that in this our course, we are simply going to use the if use in computing this, so we don't have to worry ourselves with the understanding for this complex mathematical equation. In our earlier sessions, we made mention of the autocorrelation test being a test to identify whether the market is efficient, that is the test for the efficient market hypothesis. Here we are saying that a positive autocorrelations in squared returns suggest that a higher chance of high volatility in the next period if the volatility in the previous period is high, or a lower volatility in the next period if the volatility is low. The autocorrelations of squared returns test whether the variance of the returns is potentially predictable. That's whether the market is efficient or not. Because if we can predict the return series, then we are saying that the market is not efficient. But if we cannot, then the market is truly efficient. The correlations in squared returns are shown in figure 1.12. So in our figure 1.12, we see that this is a time series plot of daily return series of the Ghana Stock Exchange All Share Index. You could see from the figure 1.12 that there are two different panels, that's the upper and the lower panel. In the upper panel, we have a squared returns. In the lower panel, we have absolute returns. You could clearly see that in the upper panel, there is less of a volatility clustering. So meaning you cannot predict. There was an absence of volatility clustering, given that we there is some form of elimination, or compared to the lower panel, which consider the absolute returns, the upper return, which is the square returns, perform better in terms of autocorrelation. With respect to the lower panel, you can see that there is some series of volatility clustering, indicating that higher volatilities in the period are followed by higher volatilities, and lower volatilities like this one, like this portion, are indicated or are shown by a lower volatility, indicating that the squared returns are better in terms of estimating for autocorrelations than the absolute returns. The variance ratio test. As we have early discussed, the efficient market hypothesis indicates that the price of a financial asset encapsulates all available information. So we are saying that the current price of an asset has all the information on that price, or on the price of that asset for a particular day. So previous prices cannot be used to predict current prices, or current prices has in no way able to predict future prices. So consider equation 1.13. We are saying that this is a simple model of asset prices, where PT is the current price and PT minus 1 has to do with the previous prices. We are saying that A, or alpha, plus mu, or ut, is the equation for return series. So we are saying that RT, which is the return series, is equal to the alpha, which has to do with the compensation for holding risky assets, which is a small compensation, and the UT has to do, which we call the disturbance term, or the disturbance term, or the error term, has to do with the other information or other factors that affect the return series that are not being explained by the alpha term. So the main implication of this model is simply that the predictability of asset returns and price depends solely upon the characteristics of the disturbance term, which is the other information which are not contained in the alpha term, which is the compensation. A formal test of asset return predictability could be developed based on the concept of a variance ratio test for autocorrelation. So we are saying that we can use the variance ratio test or analysis to test for autocorrelation, or the existence of the autocorrelation, or the idea is that we want to see the efficiency of the market. Therefore, the variance ratio test will help us to do so. The variance ratio test is designed to empirically evaluate or test the evidence of random walk or against random walk restriction. The null hypothesis of the variance ratio test is that there should be unity for all levels of aggregation, and this can be tested hypothetically using the eViews statistical application, which we are going to do so in our next session. The equation 1.14 has to do with the process that the variance ratio analysis has to go through before we will come out with the final answer or the final result. eViews illustration of variance ratio test. So here we are going to calculate the variance ratio test, or estimate the variance ratio test, using the eViews application. So it is important to make sure that before you think of starting, you have the eViews application, that is this interface. You have to have the eViews application on your personal computer before thinking of even starting the estimation process. And also the next thing you have to consider is your data. In this example, we're going to use a Ghana Stock Exchange All Share Index. Therefore, here is our data. So the first thing to consider after having the application is to launch the application. So we have to launch the application. After launching the application, we are going to have a box like this popping up on our computer, our personal computer. So we have this box, or a dialog box like this will appear on our computer. So it has several menu bars like view, procure, object, save, freeze. All these ones will appear. So here our focus is to estimate the variance ratio test. So we need our data, so we have to open the data set on our EVs application. So it's like we call it loading. We load our data set on the EVs application by double clicking on this GSC. So after double clicking on this GSC, this additional box will appear indicating that we have successfully loaded our data set in the EVs application. So you could see that here is the so you could see that our data has successfully appeared on this additional box, indicating when the data set started from and when it ends. So here we have the 1st of April 2011. So our data set started from the 1st of April 2011, and it's the last date will be 26th of October 2016. So this is the daily data set. Now, earlier discussion, we said that using the price series is not as good as using the return series, given the statistical properties of the return series over the price series, which we earlier said, or we earlier described as a stylized fact. So here, these data sets are actually in their raw state. So these are the price series, or it could be the index. So these are the prices, the raw price of the stock of the on the Ghana Stock Exchange. So in order for us to have this data set possess the or have the actual stylized or the stylized fact of a return series, so we have to difference, so we have to transform this data into a return series through the series or through the several forms of transformation. So here we have the default, where under the default you can choose to difference it, which is a simple differencing, or we can just find a way to log difference it, or any other form, or there are several forms of transformation. So whichever one we think deems or we deem appropriate, we just apply it on our data set. So here we have choose a simple difference. So we choose to difference this data set using the e-use application. So we could clearly see that after applying the difference function to this data, it has moved from its raw state to this additional state where we are no longer having figures like 986 and 1000 and above, but we are now having figures around which are mostly single digit figures like -4, 2, 1 and stuff. So this shows that the data has been different, and what is what we call the simple returns. So unlike the prices, we now have our return series, which are mostly stationary compared to the price series, which were in huge figures. Also remember that we said that price series in its raw nature are not good, or they're not perfect for analysis. So the need for us to transform the data into returns, because we said the returns has some some properties some properties that makes it better for estimation than the price series, which we refer to as the stylized facts. Remember, the focus of this study or this analysis is to calculate the variance ratio test, which will be used to estimate or used to confirm or rebut as to whether the data set has random walk or exhibit random walk. So we have to click on the view button, this button, the view button here, and on the view button additional box will appear, on which we have points like spreadsheet, graphs and etc. Because our focus is to calculate the variance ratios, so we are going to click on this additional point or button, which is the variance ratio test. So after choosing the variance ratio test among the several options available, this additional box will pop up, and in this one we have to see that there are some form of list like random walk, exponential random walk, innovations, among others. But here our focus is that we are just calculating the variance ratio test, so we just leave all these selections just as they are without making any other input or making any other changes. The output before us, or the box before us, represent the output from the variance ratio test. So here what we are saying that after estimating the model, the other thing we have to do is to interpret the output, which is we have to read meaning into it based on our assumptions and the empirical literature. We could see that the other part of this output deals with the descriptive. So here we have the null hypothesis where we say that the Ghana Stock Exchange is a martingale. So we are saying that it has a random walk or there is no autocorrelation. And it also gives us information about the sample that we included in the data or in the analysis. It also gives us the heteroscedasticity robustic, which is the unequal nature of the variance, and among others. But here our focus is on the joint test. The joint test here, this portion, our focus will be on the joint test. So we look at our value, which is 9.886. The degree of freedom, which is DF, is 741, and the probability. Here our focus is that because we have estimated, we have assumed that, or our null hypothesis was that the GAC is a martingale, or there is a lack of autocorrelation, or there is no autocorrelation. We need a probability value of more than 0.5, which is 5%, more than 0.05 or 5%, in order to prove that there is indeed no autocorrelation, or the Ghana Stock Exchange data possess random walk. But you could see, or you could clearly see from our data or from the output, that the probability value, which represent the significance level or our level of either acceptance or rejection, has 0.000, indicating that on the average we have not enough proof to indicate that the Ghana Stock Exchange is a martingale or it possesses a random walk. So in this particular test, we reject the null hypothesis. The null hypothesis was that the data sets possess random walk. So we reject the null hypothesis that this is the case, given that the probability value for the joint test is less than the critical or significance level that we earlier stated, or we earlier chose, and indicating that our data set, which is the Ghana Stock Exchange or share index data set, doesn't possess or does not exhibit the true, does not exhibit a random walk, or that there is the existence of autocorrelation within the data set. In this session, we have discussed about a random walk and its numerous assumptions. We have tested the existence of random walk with the help of the autocorrelation plot, where we indicated that the squared returns possess random walk or it has no autocorrelation. We also discussed the issue of volatility clustering, where we said that the squared returns have less volatility clustering compared to the absolute returns. And we have also tested for the variance ratio using the eViews application. Thank you.